This is an overview of our work. We propose policy adaptation from foundation model feedback to tell where the policy did wrong and help it adapt to new environments and tasks. Our goal is to train a general-purpose robot that can generalize to unseen tasks and environments instead of learning individual tasks one at a time. For example, we can train a policy on simulation data and adapt it to the real world. It is challenging because of the huge simulation-to-real gap. In this work, we focus on language condition policy. It means that the policy takes the language instruction as input and predicts action. Recently, there is a trend on leveraging the pre-trained foundation models in robotics to build general-purpose robots, and they use vision language pre-trained models as backbone encoders. So we can see that the visual observations and the language instructions are fed into the pre-trained model to encode semantic representations for the policy. So let's see the result when we train such a method on simulation data and adapt it to the real world. We find it's difficult for the trained policy to perform well in the real world. Our key insight is that while the policy cannot generalize well, the action classifier with vision language pre-trained models can still achieve a high accuracy when transferred to unseen tasks and environments. For example, in previous demonstration, given the instruction put triangle in purple bowl, the robot performed action that did not match the instruction. And when we feed the demonstration as input of the pre-trained model, it can correctly classify it as put star in purple bowl. The vision language pre-trained models can generalize well in recognizing visual concepts. In this work, we leverage this kind of generalization ability to correct the policy during testing on unseen tasks and environments. When we adapt a trained policy to a new task or new environment, we first let the policy play. That is, the model predicts and performs actions given randomly generated instruction. Suppose this is a policy trained on simulation data and we want to deploy it in the real world. We first generate a random instruction, and the robot tries to predict and perform the manipulation. We record the demonstration including the visual observations and the model's actions. Of course, the instructions and outcome actions often do not match because of the simulation to real gap. For example, given the instruction pack star in box, the robot actually moves flower shape. We then make the correction by performing relabel. That is, the recorded demonstration can be automatically relabeled by the vision language pre-trained model. Here we use clip for relabel. We formulate the task of labeling the demonstrations as visual-to-language retrieval. Given the visual observations, the pre-trained model retrieves a language instruction among all the possible language instructions. We utilize the generalization ability of pre-trained models in recognizing visual concepts to retrieve accurate instructions for the recorded demonstration. Once the pre-trained model relabels the demonstrations, we can have paired visual observations, language instructions, and the corresponding actions. We can use the data to fine-tune the policy for the adaptation to a new task. So through play and relabel, we collect the data for fine-tuning the policy in the new task automatically. After a certain number of language instructions are executed, the robot will reset the scene automatically. It will move the objects out of the container to the table following the instruction move the objects out. In this way, the robot will continue to play and explore the scene in the new tasks or environment. Let's see the result in the evaluation of scene-to-real transfer. We can see that compared with the baseline model, our model adequately and reliable can follow language instructions to perform manipulations correctly in the real world. For the evaluation of compositional generalization, we train a policy to pack objects of different shapes in the brown box and put blocks of different colors in the bowls of different colors, and adapt it to put objects of different shapes in the bowls of different colors. Given the instruction put letter I in white bowl, the trained policy wrongly picks up letter M object. And such mistake can be corrected by our vision language pre-trained model as it retrieves put letter M in the white bowl as instruction. So the pre-trained model can be generalized to recognize the visual concepts in the convolutional setting. Now let's see the result in the evaluation of convolutional generalization. We can see that our method can adapt to the new task effectively. We further designed two experiments to evaluate the auto-distribution generalization. The first one is that we train a policy to pack certain objects and adapt it to pack unseen objects. The demonstration shows that given the instruction to pack the spoon, the robot picks up a shoe. And such a mistake can also be corrected by the pre-trained model. Compared with the baseline model, our model can accurately pick up previously unseen objects during training. We also train policy on unseen environments and adapt it to a new environment with different textures and differently positioned elements. When the policy performs actions that do not match the instruction in the new environment, our model can relabel the instruction accurately, which requires both the spatial and temporal reasoning. We evaluate the model with long horizon manipulation tasks. That is, the model needs to perform 5 tasks in order. We can see that our model can successfully perform the complex long horizon tasks. That's all. Thank you.